The exams are right up there at the table. Okay, a little bit about the exam. On the bottom of the bottom right-hand corner of the second page should be the grade. And if it says something like 82 plus 2, then the plus 2 is me rewarding you for the neatness, the clarity, the way that you went in describing your answers. If you don't have a plus there, it just means that it's not bad. It's just you could maybe do a little more in like explaining what you're doing. Like maybe your math is all correct, but explaining to the reader what it is you're doing. Like, I'm looking for a plane, so I'm going to, like in words, I'm going to cross the two normal vectors, or whatever it is, just explanations. So work on that. The top one was a plus 5. I didn't make a copy. I did not make a copy this time to show everyone, but the top bonus was a plus 5. Okay? Your other mini exam is due on Monday, right? Your next one? And I'm just going to remind you of something that you'll run into on that exam. Remember from Calculus 1, this actually happens twice in the take-home exam. All right? From Cal 1, if you have a function of a single variable and you graph it and you want to know where its maximum is, then what you could do is look at the derivative of that function, right? And set the derivative equal to 0. That's how we find, that's one method that we use to find maximums of functions in Cal 1. Now there's like sign charts and things like that, and you can check to see where it's increasing and then decreasing. That's all fair game. But I'm just reminding you that if you ever have a function of one variable and you're trying to figure out where it's the largest it could ever be, you should probably turn back to Cal 1 to do that. All right? I think that's enough of a hint when you run into that issue. All right? All right, so last class we were talking about partial derivatives. I got up on the chair and I was trying to show you that if you're standing on a surface, that we can point ourselves in one direction, which would be, I'm recording, yes, parallel to the x-axis, or you could run parallel to the y-axis. Those are the two directions we like to look. And then we can point in that direction and try and figure out the slope of the tangent line in just that direction, right? I showed you some pictures. What we hadn't really gotten into is some of the notation that we use for this. So let me point out the notation for partial derivatives. If you're given a surface, z equals f of x, y, so it's a function of two variables, if we treat y as the constant, then we call the derivative the partial derivative with respect to x. And this is the way we denote it. It's f with the subscript x that tells you that x is the variable, and then xy. So it's kind of like this notation from Cal 1, right? We had this told you the derivative of f, but it was obvious from this that x was the variable, isn't it? Because it's right there. Here, if we have a function of two variables, we need to somehow denote which variable we're treating as the variable, which one is constant. So the subscript of x is what tells us that. Understand? All right, so now if we do it the other way, and we hold our x constant, then we call it the derivative, partial derivative with respect to y, and it's denoted this way. And, pardon me?
dx, dy, or is that the partial?
Yes, I'm going to talk about notation here in a minute. For right now, that's what we're going to start with. Okay, so here's an example. We're given a function of two variables, x and y, and we're asked to find the partial with respect to x at 2, 1. So before we actually get into the mechanics of it, let's talk about what's happening. I'm going to go over here. Let's say, I want to stay on camera. Let's say I'm standing at the origin, and the x-axis is this way, and the y-axis is this way. Then I'm walking out to the point 2, 1. So I'm walking two units out on x, right? And 1 unit out on y, and I'm up on the surface somewhere, right? And I'm pointing in which direction? So am I pointing parallel to the x-axis or y-axis? What variable am I holding constant here? Y. So doesn't y go back and forth this way? Yes? I'm holding that constant, which means I'm pointed parallel to the x-axis. See, if I turn it this way, then my curve goes this way, and there y is not constant, is it? Understand the difference? Okay, so I'm pointed that direction. And whatever the numerical answer is to this will represent the slope of this line. Got it? All right, so let's first start by actually just computing the partial derivative with respect to x. Now this is the notation I'm going to use, but please keep in mind that this is the same as me writing this. Okay, those are both the same thing. So I'm going to look up at this. This is a polynomial function, right? And I'm going to start taking the derivative. When I have addition or subtraction, I can just do each one individually. So I'm going to start here with y cubed. So what is the derivative of y cubed if y is a constant? If y is a constant, then y cubed is a constant, isn't it? And the derivative of a constant should be 0. So it's not 3y squared, it's just 0. Okay, plus, now what's the derivative of 2x if x is the variable? So this is just classic Cal 1 derivative now. So what is derivative of 2x? 2. And then we have this, x squared y to the 5th. Now back in a Cal 1 class, if you were doing the derivative here, you'd be doing implicit differentiation. You would actually have to apply the product rule here, wouldn't you? Yes? But here we don't. Because y is a constant, y to the 5th is a constant. And what do you do when you have a constant attached to a function and you take the derivative? What happens with that constant? It just comes with you, right? It just comes for the ride? So I'm just going to kind of cover up the y to the 5th and just ask myself, what's the derivative of x squared? 2x, but then times the constant. So I'm going to write, what? 2x, and then y to the 5th. Questions? Plus 10, derivative of 10, 0. If you're just coming in or came in a little late, the exams are right there on that table. You can pick them up. All right, so let me clean this up. The partial of f with respect to x is 2 plus 2xy to the 5th. So check this out. If I want to know, right, if I want to know the direction of this line, right, I mean the slope of this line, then what someone's going to have to give me is an x and a y coordinate. So I'm going to need to know where I am on the surface in order for me to determine that slope. And that's what's given, right? 2, 1. So what is the partial derivative at 2, 1 equal to? So 2 plus 2 times 1 to the 5th, right? That's all you're doing, plugging in 2 for x and 1 for y. And what is that? 6. Okay? That means on that surface, at that point, this is a slope of 0, isn't it? Flat? Slope of 6. So it's pretty steep, isn't it? I'm at a pretty steep incline when I'm at that point. If I were to be standing here and try and walk that way, I'd be walking up, wouldn't I? On the surface. And if I turned around and went back the other way, I'd actually be going down. All right, let's see the difference between that and the partial with respect to y at the same point. So the partial with respect to y, I'm going to come in here. Y is now the variable, x is now the constant. So when you take derivative of y cubed, 3y squared. Now it's 3y squared, right? And then the derivative of 2x is 0 plus. And then here we're treating x like a constant. So x squared is a constant. So I'm just going to kind of ignore it and take the derivative of y to the 5th, which is 5y to the 4th. And what I'll do is I'll put that 5 out in front. I'll still have the x squared that I had covered up, and then y to the 4th. And then plus what? 0. So this is just 3y squared plus 5x squared y to the fourth, and we're done. So if I want to plug in 2, 1, let's see if we get a different slope. 3 times 1 squared plus 5 times 2 squared times y, 1 to the 5th power. You got 23? Yes? Okay, 23. So that means now that if I had walked out to that point, out 2 over 1, but this time not point that direction, point this way, parallel to the y-axis, my slope is actually 23. It's even steeper that way, isn't it? So if I'm pointing that direction, it's only 6, but if I point this direction, it's 23. One interesting question would be, let's say you're standing on some surface, and you want to know which way do I point so that I would go the steepest ascent. So like in that problem, going that way was 6, going this way was 23, wasn't it? Right? But is there some other direction that I could point where it'd be even steeper? And that's called the gradient vector. And we'll actually get to that later. But there is a way to find which direction that's going to happen. It's the direction of steepest descent. And then you might ask yourself, well, which direction do I point in so that I don't go up or down? Right? Where I don't move up and down. So I want to be able to walk along the surface but never change my altitude. And keep walking around the surface like that. Imagine what that would look like. Like, I don't know, like let's say you have a mountain and you're standing here on the mountain. Right? The mountain is a surface. If you wanted to know which direction to go so that you don't move up and you don't move down, then what you'd be doing is moving around the outside edge of the mountain, right? Go around the backside or along some path and come back around, right? But you never change altitude. That's what we refer to as a contour line on a map. You know, these contour maps, that's what those contour lines are. All those lines represent the same elevation. So that would be a contour line. As opposed to a different direction, which would be telling you, this is not red, but you know, which way to go so that you go up the mountain the fastest. It's all connected to this. We're not there yet. I'm just trying to show you where we're headed. All right.
Can you take partial integrals?
Yes, partial integration. It's coming. Yep. Yep. Careful what you wish for. Okay, so let's look at this one. This is a good problem because that last one was a polynomial. Polynomial functions are easy to take derivatives of because it's just power rule. This one's going to be a little more involved. So let's start here. We want the partial with respect to x, partial with respect to y. Those are two different problems. Let me start with the partial with respect to x. Treating y like a constant, right? First of all, we have sine of a bunch of junk, right? So we have to take care of that first. What's the derivative of sine of something? Cosine. So I have to start by writing cosine of the argument, xy over x squared plus y squared. Okay, that's chain rule, right? Now times the derivative of what's in here. But remember, y is a constant, right? What the hell is that? Is that the vent? Okay, so y is a constant. So how are you going to find the derivative of this? So you brought the bottom one up and did product? So you could do that. Let me just, if you ever get stuck, okay? If you ever get stuck, like what do I do? Just replace y with some constant, and that might help you. Just come over here on the side real quick. I'm going to let y be 4, okay? Just to help me see what this would look like. 4x over x squared plus 4 squared 16. If you were asked to find the derivative of this, you would probably use the product rule, bringing the bottom up, but I think most people would probably just do quotient rule, which is product rule is quotient rule. Or you can always turn a quotient into a product is what I should say. But I'm going to do quotient rule on this, right? So you do derivative of the top, right? times the bottom minus the derivative of the bottom times the top all over the bottom squared, right? That's what it would be. So what would the derivative of the top be? 4, right? So look back over here. The derivative of the top here, because y is a constant, it's going to come for the ride. The derivative of x is 1. So you get 1 times y, which would be the first part of it, right? Do you all see that? So you have y times the bottom, right? Without a derivative. Minus, now the derivative of the bottom. So good thing there's addition between these. Let's go back over here. If I did derivative of the bottom here, it'd just be 2x, right? Same thing here. 2x, and then plus, this is a constant, right? So goes 0. So all you have here is what? 2x. It's addition between them, careful. So 2x plus 0. And then times the top, xy. I don't need that in parentheses, but I'll put it there. And then the entire thing over x squared plus y squared squared. And I'll try and do a little cleaning up here. Does anyone have any questions over where any of those pieces came from? Up here? Let's see, I'm going to have x squared y, that's distributing, plus y cubed, minus 2x squared y. All right, that's really annoying. Has that been here like all semester, that sound? I've never heard that before.
No.
Weird. The magic stick, yeah. All right. So this becomes, I know that song. All right, so this becomes these two, right? So how about this? Is that okay? We good? Yes? I think that's, can we do anything with that? No, I don't really think so, right? I mean, you could factor a y back out, but then you'd have y squared minus x squared.
Don't we leave it as that though?
Yeah, we're just, leave it as what? This?
Like, that's okay?
That's okay, yes. But what I was concerned about was what if this was a plus?
Then you could cancel.
Then a y could come out and then you could cancel one of those factors if it had been a plus. So we just need to pay attention to something like that. That's good enough right there. Why don't you try the second one? You do that on your own. See if you can do it, and I'll write the answer up here for the second part. No questions, though? Okay, try the second part. raise your hand when you're done. Just kind of give me a show of hands. You don't have to keep it up.
I know.
Okay. All right.
Wouldn't that be x cubed plus xy squared when you distribute the x?
Where?
Would you the y squared? X cubed y squared?
X cubed. Hold on. X cubed. Where are we? Here. X cubed. Oh, x cubed plus xy squared. What the hell did I do? X cubed. Right here. Thank you. Yeah, that didn't look right. It should look very similar to the last one. Good or no? Yeah? Anyone have any questions on where I got any of this? Okay, so I mean, the only thing you can do to get better at this is just practice, right? So the homework does give you that opportunity. I'm up to date on homework up through this section. I wasn't able to start 11:4, so I plan on Friday to do that. And just FYI, tomorrow I will not be in my office tomorrow morning. I've got an appointment in the morning I can't get out of, so my apologies. But I'll be there on Friday if anyone needs to meet with me. Just let me know you're coming. All right, so now some notation. You remember with, boy, that's not very good. Remember with derivatives, you know, we used different sorts of things. If y was equal to f of x, we said like y prime meant the derivative. We could write f prime x. We could write dy dx. Remember these different notations for the derivative in Cal 1? We have the same sort of thing when it comes to partial derivatives. You know, this is the same as this, which is what I was just using. And then this right here, which is not dy dx, okay? This is partial. The reason, the way that you know it's the partial is we use this symbol right here. Anyone know what that symbol is called? No, no. Look it up. I'm pretty sure it's called del. Del. Not delta, but del. But it's related to delta because it is a change. But it's the difference between a partial derivative and a classic derivative from Cal 1 is this. The classic derivative, you had one independent variable. Or sorry, yeah, one independent, one dependent. So y depended on x, so it was a straight up derivative. Whenever you have a function like f that depends on more than one variable, then it becomes a partial derivative. You have to hold one of the variables constant in order to define a derivative. So that's why we use that notation instead of the other. Also, you could use this, partial of z with respect to x, if we're saying that z, I think it says up there, z is equal to f of x, y. You can also do a partial as like an operator on the outside, the partial with respect to x of the function f, or you can use f sub 1. F sub 1 means the partial with respect to x. How in the world do I know it's with respect to x if there's a 1 there? Because 1 is always x? It's the first variable, exactly. Who said that? I heard it, okay. That just means that, look, you have, this is your first variable, right? This is your second variable. So f sub 1 means the partial derivative with respect to the first variable. Remember, these are ordered, right? X and y, you can't interchange them, y and x. So, and then you can have capital D Capital D sub 1, same concept. This just means derivative or differential. This is the differential of the function f with respect to the first variable. And then finally, capital D sub x of f. So these are all these great different notations that we can use. All right? Why don't we just like to use one notation? I mean, just all stick to the same notation. We like to make life difficult, right? A lot of it has to do with the fact that, calculus was born from two different people, Isaac Newton and Leibniz. So they both used different notations when they were creating calculus. So when their ideas came together, we have two notations. Sometimes the Newton notation is better than Leibniz. Sometimes Leibniz is better than Newton. It just depends on what you're trying to do. All right, so if we're going to talk about derivatives, then we may as well talk about higher order derivatives like first, second, third, fourth, right, nth derivatives. So we have to have some notation for this, and this is a little tricky. Here's the second derivatives. So when I have a function of two variables, right, let's say I have z equals f of xy, then I could take that function and I could take the derivative with respect to x, couldn't I? Yeah? And then get an answer. And then take the derivative again with respect to x and get another answer, right? That's what this first notation is. First, take the partial with respect to x. Whatever that answer is, take the partial with respect to x again. But instead of writing it that way, we just go f sub xx. Or f, that's supposed to be subscript 1, 1. Or look at this notation. The partial of f with respect to x, you do that first, then work your way out. Partial with respect to x of that answer. This notation is also acceptable, where you put the squareds. Now, why are these squareds offset? Like, why is there partial with respect to x squared here, but here it's partial squared and then f? Why are they offset like that? Just for craziness, just for fun, just because, yeah, why put them, let's make it even more confusing. Let's offset the twos.
It's similar to that, the next one.
Yeah, you're just kind of multiplying them together.
Yeah, it's kind of like multiplication. Yeah, I guess you could say it that way. But think of it this way, though. If I wrote partial of f with respect to x squared, what does that mean? That means take the derivative with respect to x first, and then square the answer, right? And if you looked, if someone wrote this down, squared like that, putting the squareds both here, you might think they mean that. Because you might say, okay, if they're both squared, then I'll just, square both and it's squared. By offsetting them, it means that they're two separate derivatives. Understand that? And then this is the same exact notation, but instead of using f, we're using z, because z is defined to be f. That's the first type of second partial you can have, where you've taken the derivative twice. You could also have started by taking the partial with respect to y and then following it up again with y. And this would be the notation. But there's nothing stopping you from doing the partial with respect to x, getting that answer, and then following that up with the partial with respect to y. Or the other way around. Do the partial with respect to y first, and then the partial with respect to x. Do y'all see these? There's four different types of second partial derivatives. If you have a function of two variables, there's four different second partials possible. But pay attention to some notation here, because I personally think this notation is a little tricky, especially on something like this. If you do this right here, what derivative do you take, or what variable do you take the derivative with respect to first? X, right? So you look at this and you read it from left to right. You do it with respect to x, then y, right? But if you come over here and look at the notation here, it's backwards, right? From over here. And the way you read this is more like this. See, the one on the right is like the inside. You do that first, and then the y is on the outside. So just be careful with that notation, because I think those can be a little tricky for students to remember that. Do y'all see it? All right. don't worry, we're gonna have some sort of reason for these and meaning and like, what was second derivative in Cal 1? What did the second derivative tell us about in Cal 1? Concavity, right? Whether a function was concave down or concave up. This is actually going to have something to do with that also. And this right here, these are going to help us find the highest points on the mountain or the lowest points in the valley. I mean, that's what kind of the whole goal of this is if you got a surface, we want to be able to try to find the highest points and lowest points on it, maximums and minimums. And these are going to help us do that. But we need to be able to compute them first. Find all second partial derivatives. So they're asking us for 4 different derivatives here, aren't they? 4 different ones. I'm not going to do all 4. It'll take me too long. So I'm just going to do 2 of them. So let's do fxx. The other one we could do is fxy. We could do fyx. We could do fyy. So I'm going to choose to do 2 of them. I'll do the first one. I'll do these 2. Is that all right? And then I'll leave these for you. Is that okay? All right, so let me find fxx first. So what I'm going to do first is find the partial with respect to x. Let me do that first. So you help me out. What's the partial of this with respect to x? Go ahead, spit it out. What do you got? 2x plus 0 minus 30 x squared y squared. Yeah? Hopefully you follow that. And now, yeah? That's okay? All right. And now take the partial with respect to y of this. So what's derivative of this right here with respect to y? You're treating x like a constant now, right? So that's 0, isn't it? And over here, you're treating y like the variable, x is a constant. So this is all a constant here, isn't it? And what's the derivative of y squared? 2y. So 2 is going to pop out. I'm going to get negative 60. X squared doesn't change, and y squared is now just y, isn't it? So negative 60 x squared y. That is this partial. Oh, why did I do fxy? Why did I do fxx? I should have done that one first. Oops. That's this one. I'll do fxx now, all right? Okay, fxx, 2. Oh, 2 minus, so you're taking derivative of this, that's 2, derivative of this, negative 60 x y squared. So that's 2, and then here we ignore the y squared, derivative of x squared is 2x, pops out. Here we go. Y squared comes along for the ride. Okay? Good? Do you think you can handle the other 2 on your own? Yeah. All right, good. I'll let you. I wonder if these 2 are the same. If the order matters. Yeah, you wonder, or yeah, it does? What do you think? You think they're the same answer? Do you think the order is going to matter? We'll see. Clairaut's theorem is going to answer that question right now. If f is defined on a disk, so remember these functions that we have right now are going from 2-dimensional space into 1-dimensional space, right? We're taking our input lives in R2. The output lives on a number line, right? I've been trying to stress this for a while. We can visualize this as a surface, can't we? This is saying that if your function is defined on a disk, So define means talking about domain. If you look at a little disk in here, okay? We'll call that disk D. And there's a point in here that lives in here called x naught, y naught. So you look up on this disk, up where the surface is, right? Coming out at us. We turn it over and then we're like that, right? So that surface, as long as there is a surface above this disk, and f of xy and f of yx, so that means the partials in both directions, as long as those partials are both continuous, meaning that they're not going to like have asymptotes or become undefined, as long as they stay well behaved on that disk, then you're guaranteed that the partials are the same both directions, both orders. If you do the partial with respect to x, then y, it should be equal to the partial with respect to y, then x. So the condition is that your function is defined on this disk and that the second partial derivatives are both continuous. So without us actually doing it, let's look back at that problem I just asked about, this one. Should, according to that theorem, should this be equal to this? Yes or no? Why or why not? Explain, please. You saying yes?
Yes.
Why? Because you did it and checks? Good.
There's no natural laws or divided by.
Yeah, there's nothing bad. This is a polynomial function, right? Last class we said that all polynomial functions of two variables are continuous everywhere, right? So the derivative, no, I don't care how you take a derivative of this with respect to x or y, it doesn't matter. It's still going to be a polynomial function, isn't it? And that's going to be continuous. And if you do a derivative again, it's still going to be a polynomial function, and that's going to be continuous. And what you need for this theorem to work is that the second partials are both continuous, and they will be. So you're guaranteed that these are going to be the same, all right? Or you can just check it. Now, there's nothing stopping us from doing just second partial derivatives. You can have third partial, just like in Cal 1, you can have first derivative, second derivative, third, fourth, fifth, sixth. But in Cal 1, really, just the first and second derivatives were the ones that really mattered, right? Those are the ones that really helped us. But there's nothing stopping us from doing a higher order derivative. So let's see if we can make sense out of what this one is right here. F x, y, y, x. So I'm going to take the partial with respect to x first, then y, then x. Let's see what we get. So first, start with the partial with respect to x. So what would the partial with respect to x of that be? We've already done this problem, right? 2x minus 30 x squared y squared. Isn't that what we got? Now the partial of that with respect to y, which is 0 and then negative 60 x squared y. That's also the one we just did, isn't it? Now let's do the partial with respect to y again. What's partial with respect to y of this?
60x squared.
Negative 60x squared. And then finally, what's the partial with respect to x of that? So what's the partial? What is it? Negative 120x. Part B asks you to do a different variation. Partial with respect to y, then x, then x. If you keep doing this, aren't you eventually going to get down to 0? Right? Aren't you? Will that always happen, you think? With a function of two variables, if you just keep taking partials over and over, do you think it's eventually going to become 0? Polynomial functions, yes. But if it's something other than a polynomial function, not necessarily. Yeah, cosine sine could turn into a mess. And that's also something you saw in Cal 1. Sometimes derivatives get nicer, sometimes they don't. Now here's an application of this. Laplace equations, differential equations. This is, you take a course in differential equations, you'll talk about Laplace. Maybe. Do you talk about Laplace a little bit? Yeah. So if you have, first of all, what is a differential equation? A differential equation is any equation that involves the derivatives of functions. So you have some function, you have an equation that has derivatives in it, that's a differential equation. Now there's a whole lot of different categories of differential equations. This right here is what we call a Laplace equation. And it's starting out by assuming that you have some function of two variables. So we've been using f of xy, but there's nothing stopping us from calling it u of xy. Equations have solutions, don't they? They should. I mean, they don't always, but the whole idea of having equations is to try and find a solution. The solution to a differential equation is actually a function that satisfies that equation. Instead of a solution like x squared minus 4 equals 0, here our answers are numbers, right? An equation like this, the answer is actually a function or a family of functions that satisfy that equation. And so what we're trying to do here is come up with some way of determining if functions will satisfy that or not. All of them which do, okay, functions which satisfy that equation are known to satisfy the Laplace equation. That's all they are. It's just a whole category. But you have to check them, all right? Here we go. Determine if this function is a solution to the Laplace equation. Is that a solution? So what you're going to check is to see if that equation that we just had a second ago is true. Now, let's point out some things about this. Here's that different notation, isn't it? The offset 2's. This means you're going to take the partial derivative with respect to x twice. You're going to get that answer. You're going to add it to the partial derivative of the function with respect to y twice. If those add up to be 0, then this is then the function you're looking at is a solution to the Laplace equation. So the question was, is this? So I'm going to need to know what is the partial of u, second partial of u with respect to x, right? What is that? And I'm also going to need to know what the second partial of u with respect to y is. Now, as much as I love that notation, what this really means is uxx and uyy, okay, which is a little cleaner writing, right? So what is uxx? Let's just figure it out right here. This is all just what I'm thinking. What's u sub x? Three x squared plus 3y squared. You'll agree? Partial again, with respect to x, 6x. Okay, now let's look at the partial with respect to y. Partial with respect to y is 6xy. And then the partial with respect to y again is 6x, right? So now the question, does this satisfy the Laplace equation? Yes or no? Does uxx plus uyy equal 0? Does 6x plus 6x equal 0? No. Well, it does if what? If x is 0. But if x is 0, then what's the function? The 0 function, and that's boring, right? That's the trivial solution. It doesn't make any sense for us to think about that. So what we're looking for is a family of functions that satisfy this. This definitely does not live in that family. So what do all the solutions to Laplace equations look like? No? I'm not going to put you on the spot. They all have the same look to them, no? Okay, we won't. Hey, remember implicit differentiation? Things like in Cal 1 where you had like y equals sine of xy, and you were trying to find what the derivative of y was, what y prime was, and you couldn't solve for y, so you just had to do this implicit differentiation. Same story here. We can do implicit differentiation, but it's partial implicit differentiation. Because look at our equation. How many variables does it have? 3. Right? You cannot solve for z here. Look, if you look at this, you cannot get z isolated. Well, you could, but then the z would be on the other side. So there's really no way of getting z isolated. Do y'all see that? So there's no way you can write z as a function of x and y. But we know that all these variables are connected together, don't we? In fact, if we have an equation that involves 3 variables, what does that draw? Should be a surface, right? Could be a sphere, could be an ellipsoid, could be a hyperboloid, or all these different things, cones, right? Now this one actually doesn't fall into any of those categories, but it's a surface. How is a surface, a general surface, different than this sort of thing? This is very fundamental. Let's see if you can connect this. Like, what is the difference between that and something like, if I graph these, what's the fundamental difference? Are they both surfaces? Yes. This one, though, is special because you could solve for z, right? It doesn't have to be flat, though. This could be wavy around like a blanket in the room, just kind of free, just wave a blanket and then freeze it, and then whatever it is, that's our surface, right? So this is like some wavy surface sitting here in 3-dimensional space, right? Here's the ground, and for every point we plug in, we pop up and we hit the surface, right? Think of like a vertical line test. If I were to sit here and take something and punch through this surface, I'm going to go down, or maybe I should start at the domain and go up. I'm going to hit that surface, right, in one point, and I'm never going to hit it anywhere else again, am I? Over here, though, what would happen? That's a ball, right? Surface. If I were to take some point and go up, I would punch out, right? I'd punch out of the ball. But if I went down, I'd punch out of the ball too. Do y'all see that kind of fails the vertical line test? Like a version of the vertical line test? This is not a function of x and y. This is. See the difference? But, yes or no?
Yes.
Okay, but does it make sense to you, there's a red marker, does it make sense to you that we should still be able to stand on that point and then look down parallel to the x-axis and find some tangent line slope there? And does it make sense that we should do it the other way too, pointing in the direction of the y? We should be able to do that still, shouldn't we? Even though there's another point on the other side. We should be down there and be able to point, parallel to the x and y axes and still get 2 different answers. Yeah? Our way around this trouble is implicit differentiation. It allows us to still pick these up, even though this is not a function of x and y anymore. All right. I'm wondering if y'all are really connecting this. I'm not sure. I gotta take you back, because whenever I get the feeling like y'all are just like nodding to agree with me, I feel like I have to go back. Look, y equals f of x cal 1. Can you find the slope of the tangent line? If it's a function of x, can we find the slope of the tangent line? Yes. Okay, if it can't be looked at as a function of x, like here it looks like a circle, it still is reasonable for us to ask about the slope of tangent line here and tangent line here, isn't it? The way we did that is we did implicit differentiation on this. That's how we were able to find it. Can anyone tell me what the derivative of this is implicitly with respect to x? So what's the derivative of y with respect to x here? What would we do? Derivative of this is 2x Very careful here. What's the derivative of y squared?
2y.
2y, y prime, or dy dx, depending on your instructor. I'm going to say y prime. And then equals derivative of 1, which is 0. And then you move things around. 2y, y prime equals negative 2x. You divide through by 2y. This looking familiar? And you get y prime is equal to, what is that? Negative x over y. Right? That's what you would get. So what this said is that if I want to know the slope of the tangent line on this circle, you're going to have to tell me what? Not only the x-coordinate, but the y-coordinate. And so if you tell me the x and y coordinate, like someone tell me the x and y coordinate at that point. What's the x and y coordinate at that point if this is the unit circle? What's that point right there? Unit circle. Root 2 over 2, root 2 over 2, right? Yes? Plug those in to here, and what do you get? Root 2 over 2, root 2 over 2. What do you get? Negative 1. That's the slope of that line, right? Now, what if you plug in this point instead? What's the difference in their coordinates? Root 2 over 2, but now negative root 2 over 2. And if you plug that into here, now you get positive 1 and near this line. You see that? So that's what implicit differentiation allowed us to do. It allowed us to find slopes of tangent lines on things that were not functions. That's exactly what this is doing. It's saying, hey, look, this is not a function of x and y anymore. It might be an ellipsoid. We can still find slopes of tangents on there as long as we can take the derivative, and we'll do it implicitly. I hope that helped. All right, so we're going to do it. We're going to start with this one. Partial of z with respect to x. So what this means, z is the function itself, right? We're assuming that z here depends on x and y. We just can't solve for z. The x tells us that we're going to treat x like a variable, independent variable, and we're going to let y be constant in the problem, right? That's what this means. So what I'd like for us to do this, right? That's what I'm about to do right here. I'm going to look at this equation. I'm going to take the derivative on both sides, partial derivative with respect to x. So what would the derivative of x cubed be with respect to x? 3x squared, just like we think, right? What is the derivative of y cubed with respect to x if y is a constant? 0? Well, 0. Plus, now, what is the derivative of z cubed if y is a constant and x is a variable, and we're saying that z depends on x? 3z squared times z prime, which now we're going to write, instead of z prime, we can't get away from it now. Partial of z with respect to x. See, this is the z prime. But we need to be specific now because we have more than just two variables now. Or we have, x and y. It was kind of easy to just write y prime because there was no confusion. Now we need to be a little more specific. Any questions on that? That's derivative of y cubed. Z cubed, sorry. What's the derivative of this in here? Oh, shit. What's a constant? Let's see what's a constant first. Y is a constant. 6 is y and the 6, right? So I'm just gonna bring those out. 6y, right? That's a constant. I'm just going to say forget that. It's just coming along for the ride. So what's left here is x times z. What's the derivative of x times z? Product rule. You have to use a product rule because they're both variables, right? X is a variable and z depends on x. So do a product rule right here between x and z. What's the derivative of x? 1 times z plus, what's the derivative of z? Partial z with respect to x times x equals, we're done, right? We're done with this? Equals what? Derivative of 1, which is 0, right? That might be off the camera, so I'm going to put my 0 on this side. All right, let me try and clean it up. 0 equals 3x squared. This is gone. Plus 3z squared partial z with respect to x. I'll distribute through here, plus 6yz plus 6xy partial z with respect to x. Did I distribute properly? Everyone agree with that? And what did we do when I was showing you that circle one just a second ago and we did the whole partial thing? Didn't we isolate the y prime? We got it by itself on one side of the equation? That's what I'm doing now. When I isolate the partial z with respect to x, which is what I was trying to find, right? Let's get that by itself. So why don't we move everything else that doesn't have that to the other side of the equation? So let's move this, and let's move this to the other side. So we have negative 3x squared, minus 6yz equals 3z squared partial z with respect to x plus 6xy partial z with respect to x. Why did I do that? Why did I move the stuff that didn't have the partials over? Why did I do that? So I could factor out, right? I'm going to factor out a partial z with respect to x out of both of those. So we have left side is negative 3x squared minus 6yz equals, when I factor this out, I guess I'll put it in the front, doesn't matter. Partial z with respect to x, and then I have 3z squared plus 6xy. And finally, divide both sides by what's in parentheses here. So negative 3x squared minus 6yz over 3z squared plus 6xy equals partial z with respect to x. Good? So remember I just gave you the example of the circle in two-dimensional space, and I said, hey, look, if we want to know the slope of tangent line, we actually have to know the x and the y coordinate because those are going to give us two different values, right? What we're saying is if you're sitting here on this surface and you're out there and you're trying to figure out the slope of the tangent line, here we're going to be running parallel to the x-axis because that's what that means. Then this surface could actually fold over and there could be another part below. So I'm going to need to know a little bit about where you are. And is that obvious from this? What are you going to need to know to have this partial? The x, the y, and the z. You're going to need to know exactly where you are in order for me to be able to spit out the answer. Understand? All right, I will leave the other one for you as an exercise. Not for right now, but everyone understand that's different, right? That's a different implicit differentiation. And that is the homework assignment that goes with that. And that's what I just finished today. I just posted the video. It's not a real tough assignment. Well, God, I keep on saying that. It's easy. No. It's not the first time you've seen integration type problems, you know. When you're trying to learn like integration by parts and all that, it takes like some beating to death before you get it. This is more like once you see it, it clicks. It's pretty straightforward. Let me see where we are here on our calendar. I haven't looked at this in a while. What's today? 17th. That's all we're supposed to cover. So This is going to be a very short section. When we finish this, I'm not going to push forward anymore. I think that'll be probably enough. And I'll let you all go if we end a little early today. Or maybe we can stay, hang around, do quiz or something, whatever. Tangent planes. So we talked about this last class a little bit. Tangent planes. What do you need to define a plane? Point and normal vector, right? Point and normal vector. In fact, we've seen that the equation of a plane do you remember this equation of a plane that I gave you all way back in the day? That the ABC out of that was the normal vector, right? Came from the normal vector. The normal vector of the plane, or I should remind you this way. Remember this one. Ax minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Remember that equation? There the normal vector was ABC. Now look at what I have here. A tangent plane to a surface. So we have some surface living there in three-dimensional space. Right? If we've got this surface and it has continuous partial derivatives. I misspelled continuous. It has continuous partial derivatives. Then the equation of the plane, which is tangent to the surface at a given point, is given by this right here. Does that look complicated? What does that look like to you? Does that look complicated? This right here, well, look, they have to give you a point, x naught, y naught, right? That's given. You have to be standing on a point on the surface. Maybe it's the point 2, 1, like we were at 2, 1 at the very beginning of class. I came out 2, I went over 1, right? So let's go back to that. If I go out 2 and I go over 1, we said that pointed in this direction it was 6. This direction was 23, right? Remember that? What this is saying is that, well, if I'm pointing out 6 this way and 23 this way, what is the equation of the plane that is tangent to that surface at that point? Well, here's the equation of the plane. It looks very similar to what I just had up here. This is the A, this is the B, and C is what? Always going to be -1. What is C? It's the z component, right, of the vector, the normal vector. -1 is pointed straight down, isn't it? So that's how these partial derivatives come into play in this equation. You're just going to have to figure out what the partial derivative of the function is with respect to x. You're going to plug in the point 2, 1. That's going to be a number, isn't it? That number is the first number in the direction vector for that normal. And then the partial with respect to y, plugged in the 2, 1, that's going to give you this part. And then the good thing is c is always -1. So that's what I'm saying here. The normal vector is just this. Let's see if we can do an example. When I talk, let's talk before we talk about tangent planes. Let's just clarify from Cal 1 tangent lines. The idea of a tangent line from a circle, right? When you first learn about tangent lines, how would you describe to someone what a tangent line is off a circle? How could you verbally explain to someone what a tangent line is? It touches it at one point. It is a line that touches the circle at just one point, right? So if I draw 2 points, obviously there's a line that goes through those. That's not the tangent line. If I move this point closer, then there it is, right? But I'm looking for the line that only goes through at one point, right? Which would be that. There's only one line that does that, right? That's the tangent line. Now, you could also say that that tangent line is perpendicular to the radius, isn't it? Any tangent line that you draw will be perpendicular to the radius. Now, the reason I'm asking you to think of this is because back now when you looked at Cal 1, you had a function that went like this. And we were asked to, let's say, find the slope of the tangent line here, or find the tangent line there. Can you still use the same definition that it only touches the function in one place? I mean, do we all agree the tangent line looks like it should be about like right there? Now here, it's just going to touch at one place. But back here, doesn't it hit? So you can't use that same definition like a tangent line at a point is a line that touches the function at just one point. You could say that in some little neighborhood, right, it only touches at one point. But you can't say on the entire domain of the function it only hits at one point. So when we talk about tangent lines, we're just looking locally, aren't we? Yes? We have the same idea here when we're trying to find the equation of a plane which is tangent to a surface. We're saying just at that point, locally, it touches the surface at one point. Maybe somewhere else it might hit, but locally it's going to just touch. Let me extend everything now, this picture and this picture, into 3D. Here, if I ask you to tell me about a tangent plane, just imagine putting a sheet of paper or a flat piece of cardboard on top of a basketball, right? That plane would be touching right there at the North Pole, right? And that would be tangent to the ball because it's only going to be touching the ball right there at the North Pole, yes? But if we look at the surface in general, then see, this is where it becomes very difficult for me to draw this. We have this three-dimensional sheet of paper flying around. I pick some point, there's some tangent plane there. It's just going to touch that surface at one point locally, but it might punch through the surface in other places. That's okay. So we're trying to find that for this surface, all right? All right, so let's do it. What do you need to be able to do this? You need a point and a normal vector, right? You're going to find the equation of a plane. Equation of a plane requires a point and a normal vector. That's what you need. The point we have, right? The point is the point 1, 2, 1 that's given to us in the problem. And so all we need really is the normal vector. But the normal vector comes from the partials, doesn't it? So we just said. So let's take some partials. What is the partial of this function with respect to x? 1/2 y. Okay. What is the partial of this function with respect to y? Because we're going to need them both. We may as well get them now. 1/2 x. And I'll write the definition up here, even though it's in your notes, which I know you all bring those to class and follow along every day. Right? That's what the normal vector looks like, right? So for us, it's the partial with respect to x at the point what? 1, 2. Where are we getting 1, 2 from? The x and the y here, right? The z doesn't matter in terms of this, right? Oops. So 1, 2. Then partial with respect to y at 1, 2 again. And then -1, we don't have to worry about that. We good? Let's go ahead and plug those in. What do you get when you plug in 1, 2 into the partial with respect to y? With respect to x. You get 1. And then what happens if you plug 1, 2 into this one? 1/2. And then -1 we don't have to worry about. There it is. So I have the equation of the plane, don't I? It is exactly this is A, B, and C. So A, 1, times x minus, what's x naught? The point right here, 1. And then what? Plus b, so plus 1/2 y minus 2. And then plus c, but c is -1, so -1, z minus z naught, which is 1, equals 0. And I'm going to go ahead and expand this all out. X minus 1 plus 1/2 y minus 1 minus z plus 1 equals 0. X plus 1/2 y minus a z equals 1, I believe. That's the equation of the plane, isn't it? If I graph this plane, it should touch that surface at that point, and it should be tangent to the surface there. Remember, it's always okay to scale an equation, like if you didn't like that fraction. I don't know, for some reason I just didn't like that 1/2 there. These are the same, right? I just doubled everything to get rid of the half. So this is a nice formula, right? It's just a nice, quick way of finding the equation of a tangent plane. I wonder if there's a way to do it if it's not a function of x and y. Like, again, go back to that like ellipsoid. You know, like up here at this point there should be a tangent plane, but then down here on the bottom there should be another tangent plane. Shouldn't there? Something like that? I wonder if there's a way to do it where it's not a function of x and y, where it's like an implicit equation instead of an explicit. And there is. We'll get to that. So don't worry if you were worried, like, how are we ever going to do this? No, we got a way. Don't worry. Here's the actual problem we just did. All right, there it is. That's the surface, all right? That's the surface. Right now I'm sitting there at the origin. Right? This is my domain, so I'm sitting here at 0, 0. And if you look at it from the top, you can see 0, 0. And let me show you the tangent plane right there. That's what the tangent plane looks like right there. Does it make sense to you that that's the tangent plane right there? Yes? And as I move myself around, it turned on me. Don't do that. It keeps on wanting to turn. That's all right, I'll just slide it up here. Get it over here. There we go. See that point there? It's moving around. So you see that tangent plane? I'm just making sure you understand geometrically what that tangent plane looks like. It obviously cuts through the plane in many different places. I mean, cuts through the surface. But at that point, near that point, it touches just there. All right, so let's get to, where's the equation? Oh, there it is. Let's get to our answer. There is our answer right here. So let me spin it around so you can see it. That's it right there. So we're out 1 on x, up 2, and there's our plane, and there's the equation. It looks a little different than what we got, but all right. Let me see, is this the last example? Whoa, what happened? Something happened here. It is the last example. Okay, let's take out a sheet of paper. Let's put your name on it. And let's do a group quiz. Sound like fun?
So is there a little class name on it?
Everyone's gonna turn in their own, okay? And I want you to write the work down. Look at this as just like a nice gift to you. You've got 25 minutes to come up with this. It shouldn't take you that long. But let's see how you do with those partials. You're free to work together. You don't have to work together. But don't ask me if it's right or wrong, okay? Like, don't turn in and be like, is this right? I'm not going to tell you. I want you to, you can, by group, make a decision, thumbs up or thumbs down. You can talk to each other around the room. You don't have to just sit with the people you're next to. We good? I'm going to turn off the video. I think that's it. Just so it's on record, the homework assignment for this section is just numbers 1 through 6. All right? We'll pick up next class. Oops. We'll pick up next class in 11.5, which is chain rule. Chain rule.
Did you say chain rule?
Chain rule, I did. Yeah, I'll be right there. Hold on.